Have you ever imagined being completely and utterly lost? Maybe in a thick forest, or a city you've never visited before. The sun is hidden by clouds, and your phone has no signal. How would you find your way? When you hold a compass, you're told to hold it flat and let the needle settle. You watch it dance for a moment, a frantic little spin, before it slows and comes to a rest, pointing in one specific direction. It's not a random guess. If you turn your body, the compass casing turns with you, but the needle swings back, stubbornly pointing to that same spot. It has an invisible anchor. There are no batteries, no wires, and it receives no signal from a satellite. To an ancient traveler, it must have seemed like pure magic, a whisper from the gods. But it's not magic. It's a profound and beautiful form of physics happening on a planetary scale. The compass is listening to a secret conversation the Earth is constantly having with itself, and we're about to learn its language. To understand the compass, we first need to look closely at that little red needle. It isn't just a random piece of metal that's been painted. That needle is a magnet. It's a tiny, carefully balanced sliver of iron or steel that has been permanently magnetized. We say that magnets have two ends, a north pole and a south pole. The north pole of one magnet will snap together with the south pole of another. They attract. But if you try to force the two north poles together, you can feel them push each other away. They repel. This is a fundamental rule of magnetism. Opposites attract, and like poles, repel. The compass needle is no different. One end is its designated north pole, and the other is its south pole. It is balanced on a point with extremely low friction, allowing it to pivot and swing with almost no resistance. It's a magnet, just waiting to be influenced by another magnetic force. So what is it responding to? You can look all around, but you won't see the other magnet. There's nothing obvious in your immediate surroundings. That's because the magnet it's interacting with is the largest one you will ever encounter. In fact, you are standing on it right now. Our entire planet Earth is a gigantic magnet. It is the hidden force that the compass needle is so elegantly tuned to detect. You can't see it, touch it, or feel it. But this magnetic field is always there, silently pointing the way north. Why is our planet a magnet? The answer isn't that there is a giant bar magnet buried inside. The reality is far more dynamic and interesting. The secret lies thousands of kilometers beneath your feet, at the very center of the Earth. Deep inside our planet is a core made of metal. The outer layer of this core is a massive sphere of liquid, molten iron, and nickel. It is unimaginably hot, with temperatures exceeding those on the surface of the sun. This heat keeps the metal in a constantly churning liquid state. As our planet rotates on its axis, this vast ocean of liquid metal swirls and flows in complex, powerful currents. The movement of a conductive material like molten iron generates massive electrical currents. This is a basic principle of electromagnetism. The geodynamo effect turns the entire core of our planet into a natural electromagnet of immense power and scale. This magnetic field doesn't just stay inside the Earth. It radiates outward, extending far into space and forming a protective shield around us called the magnetosphere. It creates a vast network of invisible lines of force. These lines loop out from the planet's southern hemisphere and curve around into the northern hemisphere. Picture drawing lines on an apple, starting from the stem at the top, looping down and around the sides, and converging at the bottom. That's a simplified picture of Earth's magnetic field lines. Now let's return to our simple compass. It holds a tiny magnet, perfectly balanced and free to spin. It's floating, not in water, but in this immense, planet-wide magnetic field. Those invisible lines of force are passing right through it. Just as iron filings arrange themselves along the lines of a bar magnet in a science experiment, the compass needle does the same thing on a much grander scale. The north-seeking pole of the compass needle is attracted along these lines, pulling it towards the magnetic pole located in the northern hemisphere. This is where we encounter a wonderfully confusing twist, a quirk of history and terminology that often trips people up. We established a fundamental rule earlier. Opposite poles attract. A north pole pulls on a south pole. The end of the compass needle that points towards the Arctic is called the north-seeking pole, which we shorten to just the north pole of the compass. So if the north pole of our little compass magnet is being pulled towards the Earth's geographic north pole, what must be true about the Earth's magnetic pole in that region? It has to be a south magnetic pole. For a north pole to be attracted to it, the pole it is seeking must be its opposite. That's the mind-bending truth. From a pure physics standpoint, the magnetic pole located near the geographic north pole is actually the south pole of the Earth's giant magnetic field. This isn't a mistake, it's just a historical convention. Humans were navigating using the direction north long before we understood the physics of magnetism. We named the end of the needle that pointed north the north pole of the compass. For that name to make sense with the rules of physics, the thing it's pointing to must be a magnetic south. There's one more layer of complexity. The magnetic poles and the geographic poles are not in the exact same spots. The geographic poles are the points on the axis the Earth spins around. The magnetic poles are determined by the churning core, and they wander over time. Right now, the magnetic pole in the north is hundreds of kilometers away from the true geographic North Pole. That difference, which varies depending on where you are on the planet, is called magnetic declination. Serious navigators, like pilots and ship captains, must always account for it to plot a true course. This also means that compasses from a century ago are slightly less accurate today because the pole they are pointing at has moved. So the compass is a beautiful paradox. It is a brilliantly simple tool that allows anyone to tap into an incredibly complex, dynamic, and ever-shifting planetary engine. For thousands of years, people used this magical arrow without fully understanding the planetary science that made it work. They just knew they could trust it. The great insight here is that our world is defined and governed by powerful forces that are completely invisible to our senses. We cannot see gravity, but it holds us to the ground. We cannot see magnetism, but it points the way home. The simple compass teaches us that even the most humble-looking tools can be gateways to understanding the most profound scientific principles of the universe. That tiny spinning needle tells the story of a planet-sized engine. It speaks of a liquid metal core, hotter than the sun, generating a force field that protects us and guides us. It's a bridge between the small, observable world that we can touch and the vast, unseen systems that make our existence possible. So the next time you see a compass, or even just the compass app on a phone, take a moment. Don't just see it as a simple arrow pointing north. A delicate scientific instrument, a passive detector for an invisible planetary scale force field. It's a conversation with the planet. And that is how a simple compass always knows which way is north. It's listening to the deep, steady, magnetic heartbeat of the Earth